Ka pai. Tēnā koutou katoa. Nau mai haere mai ki tēnei hui a ipurangi o te kōmata o te tonga. I roto i te wiki o te reo Māori, ka tuku a te mihi nui ki a koutou te hunga kōrero Māori. He mihi nui hoki ki a koutou e hui hui mai nei I runga I te whakaaro kōtahi, te kaupapa nui o te whakamahana o tēnei ao. A very warm welcome to everyone who's joining us today in our Deep South Challenge virtual seminar. And the kaupapa of today is Clouds and Aerosols over the Southern Ocean, which is a joint project between our Earth System Modelling and Prediction Program, that just moved, Vidya, and our Processes and Observations Program. Those programs are led by Adrian McDonald and Olaf Morgenstern. I also wanted to give a warm welcome in Māori for this seminar because it's happening in the Te Wiki o Te Reo Māori, I don't know how to say that in English, Māori Language Week, and a reminder to everyone that we have a very strong and flourishing Vision Mātauranga research program as well. So a couple of things about the way the seminar is going to run today. We ask for your patience because we have presentations happening in two hubs. Adrian McDonald will be presenting down south and Vidya will be presenting from here in Wellington. And that's the first time we've had a dual presentation set up. So if we have a little hitch, then just take a deep breath and bear with us while we sort it out. We ask you all to keep yourselves muted. And when it comes to question time, we'll control the unmuting from our computers here. Otherwise, it can get a bit chaotic. So the way it will run is that Adrian will begin our presentation and speak for 15 or 20 minutes, and then Vidya will present, and then we'll have time for questions, 15 or 20 minutes at the end. We ask you to direct your questions first to Adrian, and then to Vidya, so Lucy will run that process. The way to raise a hand, there's a few ways to do that. If you're in a physical hub, you can just literally wave your hand around, and the person running your hub will hopefully let us know. If you've zoomed in on your own laptop, you can raise a hand digitally in the Manage Participants section of Zoom. And if neither of those things work, you can type a question in the chat panel in Zoom. And once or twice, if even that hasn't worked, you can email me, which is alex.keeble@niwa.co.nz. You will have received that in the registration email. So once again, thank you very much for joining us, and please give a warm welcome to Adrian McDonald.
Okay, right, so tēnā koutou katoa. Welcome to this seminar. I've got the privilege of starting this seminar but sharing with Vidya at NIWA. I should say that this isn't all my own work or Vidya's work. There's significant input from the Cloud and Aerosols team, which includes Olaf Morgenstern at NIWA, Mike Harvey at NIWA, and Roger Davis at Auckland. There's also Simon Parsons at the University of Canterbury, Alex Schudderboom, Peter Coomer, and Sean Hartry, who are all PhD students. We also work closely with the Aerosols project, the 4D drones project, and the single column model project within the Deep South. So we'll get on with things now. So just to provide some context, we're going to be talking about clouds and aerosols today, but the fundamental reason why we're interested in clouds and aerosols is associated with the energy balance in the atmosphere. So this diagram shows a kind of cartoon schematic of the incoming sunlight, which is the blue line, and the outgoing long wave radiation, which is the red line. So this is the heat emitted from the surface associated with thermal heating blackbody radiation. So we see that there's lots of sunlight at the equator and lower amounts of sunlight hitting the surface of the poles. And we have a surplus of sunlight relative to the thermal infrared in the tropics and a deficit at the equator. That imbalance across the system effectively drives the atmosphere and ocean circulation. So all the weather systems that we see over New Zealand are fundamentally powered by this differential or this imbalance. So there's significant differences between observations from satellites and climate models in the sunlight absorbed by the Southern Ocean, so this region here. So what we can see that is over the Southern Ocean, we have too much absorbed sunlight hitting the surface. And that's of the order of about 50 watts per metre squared. So if we think about our standard New Zealand quarter-acre section, about 1,000 metres squared, that's like having 50 1 kilowatt bar fires on that ground. So if you scale that up to the Earth, that's a lot of energy that is getting through to the surface of the Earth. And having that problem in the model is a significant issue. It leads to significant amounts of bias in the sea surface temperatures, and that temperature bias in turn contributes strongly to biases in the storm track, which are the fundamental process which controls most of the weather over the New Zealand region. So clearly it's a problem that we'd like to be able to solve because it has a direct impact on New Zealand's weather and climate. Sorry, just thinking about it, I might just try. So if you can move it on one picture, if I can't do that because it seems to be, oh no, there you go. Sorry. So the previous diagram was the annual average pattern. So I thought I'd show you the difference between a snapshot from the model output, from the NZESM output. This is actually the GA7 model, so it's just the atmosphere part of the model and satellite observations. So this is a nudged model run, and what that does is uses observations to push it towards the right direction, but a limited number of observations, so that ideally this is showing the amount of shortwave radiation, so the sunlight reflected off the surface or clouds. And ideally we'd like these two diagrams to look exactly the same. But what we can see is that we're missing quite a lot of cloud structures, and we can also see that the colours associated with cloud in the Southern Ocean region are slightly different. So this is telling us that the model doesn't have enough cloud to reflect radiation away from the surface, but it's also potentially the cloud properties are incorrect. So we've got two potential problems in NZESM. So the accumulation of this effect over the year causes the diagram previous. So I'm going to go to the next slide, hopefully. Okay. So now I've given you some context. I'm going to talk about the project goal. So the objective of the project is to improve the representation of clouds and cloud aerosol coupling in the NZESM. So I made this diagram a few weeks ago, and basically it identifies the process that we use in the Clouds and Aerosols program. So we do model simulations, so Vidya and Olaf run the model. People like myself and Mike Harvey and Sean and Peter make observations, and then we compare the model simulations with the observations. So we have a model evaluation pathway. We look at the model and decide how well it works or not, as the case may be, and then that feeds into thinking about model improvements. But process understanding taken from the observations also feeds into that model improvement. So going through this iterative cycle a large number of times, hopefully we get to the point where we have climate better climate projections for New Zealand, and we've solved some of this shortwave bias that's a significant problem in the model. So this is from a study by Ben Jolly that got accepted in 2018. So this is half funded by Deep South, half funded by an NSARI project called the Ross Ice, or Vulnerability to the Ross Ice Shelf project. So this analysis used a modern satellite system which had a light or a laser radar on board, and basically allows us to probe through the atmosphere and see the vertical structure of the atmosphere. So we've got 4 panels, and they identify DJF, MAM, JJA, which are different seasons. So we've got summer, autumn, winter, spring. And what we can see is that the cloud distributions change as a function of season over the Ross Sea region. But the clouds are made up of different things. So there's some ice clouds, there's some water clouds, generally near the surface, and there's also mixed phase clouds. So mixed phase clouds are clouds where we have ice, and we also have supercooled liquid water. And those are generally at low altitudes. And what we're tending to find, and what the literature shows, is that the model tends to produce too much ice cloud and not enough supercooled liquid cloud. So we're trying to work out this process. So recent studies using the NZ-ESM parent model, so the UK Met Office systems, have looked at the effect of production of ice cloud in the model, and they found that there's an important role for aerosols and ice nucleating particles in producing ice clouds in the model. So the model starts off with supercooled liquid cloud, and that's very reflective. It reflects an awful lot of shortwave away from the Earth and back into space. But the model tends to form ice, and that doesn't reflect quite as much radiation away from the Earth's surface, and therefore too much radiation, or that shortwave sunlight hits the ocean surface and warms up the sea surface. So while we're thinking about large global scale things over the whole Southern Ocean, we're also thinking about micron scale particles. So a hair's width is about 50 microns across. So we're talking about very little particles, but these particles can have a really big important role in cloud formation, and potentially have a very significant understood role in the Southern Ocean region. So what we've been trying to do, rather than just use all the satellite data and just compare averages of data with the model averages, is to target our observations and our analysis so that we can understand things more thoroughly, and that we can specifically target low-level supercooled liquid water clouds. So we've been using machine learning and cloud classification to do that. So we start off with something that looks like the image. So we've got an image of clouds from a satellite, and we do some statistical analysis on that, and apply machine learning algorithms on that statistical analysis of this data to basically identify specific clouds and their properties that we can help to feed into the climate model later on. So to start with, we change from this into a statistical representation. So this is a joint histogram. So the colours identify the probability of a certain cloud with a particular cloud top pressure, which basically tells you what the top of the cloud's altitude is, and the optical depth, which tells you something about the thickness. So in this case, we've got a high-topped cloud, because it's about 300 hectopascals maybe, and it's quite a thick, deep cloud in this case. By using machine learning, we can identify all of the relevant supercooled, low-level supercooled liquid clouds and convert that observation, or that single observation, but in reality we have many, many millions of these cloud scenes, and we put them through a machine learning algorithm, and then we can identify how common particular cloud types are. So in this case, this node I5 is associated with a certain cloud type, so it's a low-level cloud type, and it's particularly common over the Southern Ocean, and also maybe a little bit in the storm tracks and in the Northern Hemisphere. So we can effectively target our satellite analysis towards improving our analysis. And we've written a few papers on that recently. Unfortunately, satellite observations can't do everything. So cloud is difficult to detect above ice-covered surfaces, so the Antarctic and the sea ice region. So hopefully you can see Antarctica's shape in this image, but you can also see that there's large areas where you're not quite sure whether it's Antarctica or ice or sea ice. And for the older generation of passive satellites, this is a significant problem. So it's very hard to tell low-level cloud from the surface, because the temperature is the same, so the thermal response is the same, and also they're the same color as the surface. So this is a problem, which means that we've got to think about using ground-based observations as well in our analysis. Satellites also can't give us some of the detail that is really required as well. So even the most modern generation of satellites now use laser radars and radars to look down and be able to look through cloud. But even the best satellites that we can use for this still have problems seeing clouds. So what we've done here, or what one of my PhD students has done here, is taken climate model output, and they have simulated what they would observe with a laser radar or LiDAR that is looking down from the satellite and up from the surface. So the top diagram is the spaceborne satellite instrument, and what we're trying to observe is how much cloud can we see at low levels. And so in the top diagram, we can see that we don't see an awful lot of this low-level cloud from the satellite, and that's because of obscuring higher-level cloud. So that there's basically a cloud above the lower-level cloud, and therefore we can't see all of the cloud that we need to be able to see, or we can't determine its position well. Whereas when we use a ground-based LiDAR system or a ceilometer, we can see a much larger proportion of this low-level cloud. So this identifies why it's worthwhile us going into the Southern Ocean on ships to make measurements of cloud, because simply put, we can't see the low-level cloud in satellite measurements in many cases. So as part of the Cloud and Aerosol project, we've completed a large number of voyages, or put our instruments onto a large number of voyages. So we've put instruments onto the Aurora Australis, which is the Australian Antarctic Division vessel. We've put instruments onto the Nathaniel V. Palmer NSF ship, which was during the Piper's voyage. We've also put things onto the HMNZS Wellington, and we've had 3 separate voyages on the Tangaroa. We've also deployed instruments at Macquarie Island for over a year now. So by continuously making measurements during voyages of opportunity, so in the upcoming year we'll be putting the instruments onto a South African vessel to make measurements on the other side of the continent. By doing that, we can gain the detailed measurements that are going to help with our process understanding and help us improve the climate model. So the most recent voyage that we did, so it was completed in March 2018, was the TAN1802 Voyage. It had a vast array of instruments on board. So we had a micropulse LiDAR, a ceilometer, a weather radar. We had a whole container worth of aerosol instruments. We had weather balloons, we had UAVs, and they were all focused on making either cloud or aerosol measurements. The diagram above shows a picture of some of my PhD students looking on while we're just about to launch a balloon. The diagram below shows measurements from a laser ceilometer, and effectively what we can see in the latter part is cloud structure and very low level cloud structure, so below 2 kilometers nearly all the time. As I identified, there was a vast array of aerosol measurements and lots of different types of instrument, and that's because aerosol is very hard to measure. It's over a wide range of sizes, even though the sizes are all very small. So we're talking about microns to tens of microns. And a micron, remember that a hair is about 50 microns wide. So this is just showing an example of 2 instruments that are measuring nearly the same range, and they match relatively well over the voyage length. But given the fact that the tanker, or this last Tanker voyage was only in March, we're still working on that data. But we're working on that towards, in partnership with the modelers to make sure that we're producing things that are useful. Right, so we all know that field work is hard. I can see people on the videos that know all about fieldwork, and fieldwork's difficult. It's particularly difficult on the Southern Ocean, so we're going through the roaring 40s, past the furious 50s and into the screaming 60s. So the winds are not nice. It's hard work in that region. It's cold, and also during this voyage, the average cloud cover was 93%. So it was grey and horrible a lot of the time. I thought I'd just show this video of one effort associated with a UAV that we ran, because I thought it was interesting. So I'll start that off there. Oh, maybe I won't. No, can you try and press that button, Vidya? Great. So this video shows why I was very pleased that I bought a waterproof drone, basically. So the winds were a little bit too high that day, and the drone got into the water, but it made the measurement we wanted to, and we managed to get it back that time. So that was great. I'm now going to hand over to Vidya, who will ably talk about the modelling component. I will sit back. Over to you, Vidya.
Thank you. Thank you, Adrian, for the introduction. So I welcome you all to the modeling perspective of the Cloud and Aerosol project. So you got a gist of what's happening with the observational part of the Cloud and Aerosol. So now let's do a bit of modeling. So as many of you might know, one of the main aims of the entire Deep South project is to have an Earth system model for ourselves. And this Cloud and Aerosol is a sub-project of the Deep South that particularly aims in improving the representation of clouds in the climate model, which has been an everlasting issue. So what is it and why is it happening? We will see in the forthcoming slides. So as a base model for our atmosphere model development activities, we use the unified model from the UK Met Office. And in the Met Office, they have different groups for evaluation of processes, and there is one Southern Ocean Processes Evaluation Group. So as part of the Cloud and Aerosol project, we are deeply involved in contributing to the model development in that part of the world as well. So what we want to do is basically we are using their model as our base model. We try to fix the problem of this representation of clouds over Southern Ocean, which they've kind of outsourced it to us. So we are actually nailing that problem now. So what we want to do is to fix that problem, include that in our Earth system model, and then they can also implement those changes in the base model that they use there. So it's kind of a give and take agreement, and it's been going really well within this framework. So it's time for some pretty pictures. So this is like a standard schematic for what a global atmosphere model actually looks like. So for people who are less familiar with the concept of climate modeling, it's nothing but basically a mathematical representation of the Earth's climate. So what we do is we basically divide this entire planet into a three-dimensional grid box, and you just apply the basic laws of physics, fluid dynamics, etc. And then you kind of govern the transfer and exchanges of heat, radiation, and masses between those different grid points. So to make it a bit more clearer, so if you can see, you can focus on that tiny little red box there. So let's consider that's one grid box, and we call it like a three-dimensional grid box. So it should have like an X, Y, and Z plane. So X and Y would be the horizontal, the latitude and the longitude plane, which we say in terms of, so when you say that a model resolution is 1 degree by 1 degree, so it roughly translates to something like, so 1 degree roughly is 110 kilometers around equator. So 1 degree by 1 degree is that square box in the XY plane. But we also have a vertical Z axis. And within the atmospheric modeling, we say the height in terms of pressure levels. If I don't know how far the details you can see in this. So what happens is, so you can see different components in the system. So there are exchanges from the ocean to the land, and we have some land use, pattern changes. You have your ecology here. Then you have natural forcings like solar radiation, volcanic eruption, and of course we are there. So the human influence. So all these are the factors or that are contributing to the transfer of heat and other components. So what actually we do in the climate modeling is you calculate these exchanges within all these components within this one particular grid box, and then you try to see how that grid box is interacting with its neighboring points. So then you do like for each grid boxes, and then you kind of integrate it for the entire planet. So that's the basic concept of atmospheric modeling. When we say Earth system model, so this is an atmosphere model. So you have similar components like this for ocean, for land, for sea ice, for biogeochemistry and everything, because these are the different components of Earth system. And an Earth system model basically takes all these different models and they try to communicate each other under one single umbrella. So for the present talk, I would be focusing mostly on the atmospheric component. So this is just to show what exactly is the resolution of the model in terms of forecast period. Forecast period is nothing, but it's just how early you can predict an event. So in this figure, if you can see, It's basically differentiating between weather models and climate models. So it's essentially the difference between weather and climate. One is a short-term prediction and the other one does a long-term prediction. And on the y-axis is basically the grid length, or how much spatial resolution it gives. So what you want to see is like towards the left side, they are the short term weather prediction models, and our Earth system models and the climate models are up here on this side. So the space model that we use, it can be used for both numerical weather prediction and climate modeling. So you just need to pick up the right configuration. So this is just bringing back the slide that Adrian just showed some time back, that we know that we do have issue with the model, that it has this excess of absorbed shortwave radiation, especially over the Southern Ocean, as we can see as this red color. So the insulation that we get from sun, that's a shortwave range, and the Earth emits the one in the long wave range. So obviously there is an imbalance, and it's caused by something that's happening in between. So that's got to be the clouds. So why is it that cloud is having such an issue? So the main problem is this entire process of cloud formation, the growth, its depletion. So they kind of span over a variety of spatial and temporal scales. For example, you can see that there are cloud systems that actually extend over thousands of kilometers. But then the very essential, the growth of cloud, actually, it is happening on subgrid microscopical time spatial scale, because it's caused by cloud droplets and aerosols, and they are under this grid scale parameterizations. And then it's the same thing with the temporal scales as well. So you can have something that can happen in like hundreds of years, say example, once we have the equilibrium climate in the future. So that would take like long time. Whereas the growth of clouds by this droplet collision, that actually happens in a fraction of a second. So it's the same thing, but it kind of spreads in both spatial and temporal scale. So it is basically the demarcation between how much of these processes you can include in the model. That is what causes this uncertainty, or the model biases or errors, as we call. So parameterization in terms of atmospheric modeling is basically simplifying something which is overly complicated or it is too small to represent. So we do kind of parameterization and then make it simpler. It is unavoidable. We need to have parameterization in global models, but how we do it and how neatly we do it, it kind of reduces or governs the biases and issues that we face in the present day climate models. This one, what you see is basically the improvement in the shortwave radiation bias that has been happening in the model versions by far. So GA stands for the global atmosphere. So GA6 was the much earlier version, and the 7.1 is actually the upfront version that we have now. So all I want to tell you is that, so just look at the red color. Red is not good. Red means it's nasty. And let's focus on the Southern Ocean. So you can see that in the GA6, the issue was really bad. So it was up order of 35 to 40 watts per meter squared over here that we had the shortwave radiation bias. And then when it reached GA7, it did improve, but then we can still see that the problem still persists. And then the most upfront version, that's 7.1. So compared to the earlier version, there's been massive improvement, but again, it's about 20 watts per meter squared bias is still retained in the version that we have. So it is at this point that the cloud and aerosol actually kind of took over, or we are kind of exclusively dealing with this problem, and this would be the base version. So I'm not going into the details of what are the modifications that actually improved from each version, because that's your microphysics. I don't think that is the topic for today. But yeah, all I want to say is that it has been improving, but no, it's not completely gone. We need to do something about it. And why is this happening? So Adrian was mentioning earlier that we have issue with surplus ice in the model, the atmospheric ice. So it kind of hinders the proper functioning of clouds. So how is it happening? Because the property of clouds, it depends on the particle on which the clouds are formed. So ice clouds and liquid clouds, they behave differently. So in reality, if there is more liquid clouds and if the model has like surplus ice, then it would be showing the property of ice clouds in the model compared to the reality. That's not good. And we have seen from the earlier plot that we have more supercooled liquid in this part of the world. So just to explain what supercooled liquid is, so usually a liquid freezes to ice in like once it reaches 0 degrees Celsius. But there are some parts of the atmosphere that it can retain as liquid even at as low as like minus 30, 40 degrees Celsius. It doesn't freeze, but it just stays as liquid. So that's what you call the supercooled liquid. And the clouds that are formed from this, so they have a different property. So what happens in the model is that model just treats all this as ice clouds. So our main thing is actually to reduce the amount of ice in the model. So yes, there is an equation. I know nobody likes equations, so I have grayed it out so that you don't even have to look into that. So all you need to see is the factor C that we have in this equation. So this is basically what was the crucial factor. So how did we reach or arrive at this factor? So model has about 5 or 6 processes that govern the ice formation and maintenance in the model. So what we did was to have an approach of the so-called sensitivity studies. That's basically you turn off each process at one time and then you kind of quantify how much is the ice input or how much is that particular process contributing to the maintenance of ice in the model. And then you do that in combination with a couple of processes. So it's basically a trial and error game, and you just need to see which one is the more sensitive realization, and then you kind of narrow down your tuning to that particular process. So after some trial and error, we have identified that it's the ice deposition process that seemed to be really responsive in terms of the ice amount of ice in the model. So this is the equation, how it is represented in the model. So the factor C, as you can see, is what is known as the shape of the ice particle. So by default, the model assumes that the ice particles are spherical. But we know that in reality, that's not the case. We can see all those fancy ice particle shapes in the real world. But it is impossible to include everything in that in the model. So this is where actually parameterization comes into the play. And this is where we need to have close linkages with the observational studies that, so what is the ideal range of values that you can use for one value rather than testing or implementing all the available possible realizations. So we did a couple of studies by putting different values to this shape parameter. This plus also in combination with some other parameters like the temperature at which the ice starts growing in the model and things like that. So it's a combination of different parameters. So the plot that you see here, so this is provided by Alex Tridaboom, who's working with Adrian. And he has come up with a very neat metric evaluation. So you don't have to go into the details of any of the details of this color code. So this is basically the different sensitivity realizations that we did, like using different values for capacitance and in combination with the others. So all you want to see or I understand from this plot is that the closest that each of those points are to the origin, the more closest it is to the observation. And so that's the basic take-home message. So if you look, and this is the shortwave radiative effect for the global, and this is for the bottom Southern Ocean, that particular band. So if you look on the first one, so if you look at the pink one, so that looks really good. It's really close to the origin, but that's where we actually completely kill the deposition process. I mean, That's not realistic. But that's ideally where we want to have the error. So, but we have to do that without actually having to kill the deposition process. So we are in the process of bringing a model which is more suitable to this and in a more realistic way. So the details of this probably Adrian can provide at some later time. And now we want to see how does it actually, that tuning of that shape parameter, how does it affect in the ice formation in the model? What you see here is basically the anomaly of the atmospheric ice content. So what is anomaly? Anomaly is basically the difference between something that is a standard, a reference, and the one where you actually put the changes in. So here what you see is the difference in the ice content from the standard base model, which we know that it has excess ice. Then you have the sensitivity where you tune that shape parameter and some other parameters, and then you take the difference between these two, and then you look at the atmospheric ice content. So on the x-axis, it's the latitude. On the y-axis, it's the height of the atmosphere. So as I was saying, in the atmospheric modeling, it's actually the height is measured in pressure level. So roughly it translates to something like the difference from surface to say 6 to 7 kilometers above the surface. So it's roughly the lower troposphere. So we can see that there is a significant reduction in the ice amount in the model, and that's actually happening at the place where we want to see. So that is good news. So this is what we were trying to do, how to reduce the amount of ice in the model for that part of the world. And then yes, so that part is doing good. Blue is less. Okay, so we managed to reduce the ice in the model. So does it mean that we have more supercooled liquid for that part of the world now? Because that's how it should be. Observations say that we do have more supercooled liquid. So in the next slide, that's exactly what we are saying. So this is exactly similar to that of the earlier picture, but instead of the ice content, what we are looking at is the supercooled liquid content anomaly. So again, we can see that in that part of the world, we do have an increase in the supercooled liquid, which is good. So far, so good. Now we want to see how much this has an effect on the radiation biases. So earlier we saw that plot with 3 generations of the model. And then you can see the top one is the one where you can actually, it's where we use the new model with its changes in the parameter, and then you take the difference. And this is just a reference for the earlier run. And you can see that over the Southern Ocean, it has improved significantly. The radiation biases are actually in the shortwave. So this is the top of the atmosphere shortwave radiation bias, and it has tremendously improved. So it's like a good start. So we have actually managed to nail the ice process and then reach here, which is good. But is it what we want to achieve? So we were by far focusing on the red color on the Southern Ocean, or our part of the world, which has been improving. But what about the rest of the world? There is red everywhere. So you can't just fix something at the cost of some other things. So you definitely can't say that this is the end. And this is actually where the aerosol bit of the Cloud and Aerosol project comes into being. So why is this happening? And this could be because of the insufficient representation of aerosol in the model. So I would like to show the conclusion in 2 parts. So one with a slide with text and the other with an animation. So this one, just to wrap up, yes, we had excess ice in the model, so we had to find a way to reduce the ice content in the model in a more realistic way. And with the help of observational data and also with some metric evaluation and things like that, we did manage to find reach that goal. And then you see that, yes, we did reduce the radiation bias over the Southern Ocean, but of course, there are other places that needs attention. So our next step is basically to identify those physical processes that are actually creating this difference in the radiation biases over 2 hemispheres. And one of the ideal candidate is the so-called ice nuclei or the freezing nuclei. So that is basically the particles that you can find within the supercooled environment that kind of triggers the ice crystal formation in the atmosphere. So we don't have that much of ice nuclei over this part of the world, but we do have a lot of supercooled liquids. So how do we deal with it? And this is exactly where we have tremendous need of more observational data to find out what are the potential candidates of ice nuclei in this part of the world. So this is just the last slide to show you. So this is what the global distribution of aerosol looks like. So the most eye-catching feature here is that there is a difference in the distribution between the two hemispheres. So the red color is the dust. So you can see that coming out from the Sahara and other regions. And then you have the organic and the black carbon that's also mostly concentrated on that part of the world. Then you have white as the sulfates, and then blue as the sea salt, which we find abundantly over this part of the world. But whether or not these are ideal candidates to be considered as a freezing nuclei, that's probably a discussion for another day. But yeah, to wrap up, that's the process's stand as of now. Thank you.
Thank you, Adrian and Vidya. It was great to see how those two parts of a project fit together from different programs. We're just going to open the floor. As Alex said in the beginning, we'd like to try and take questions for Adrian first, just so we're not flicking backwards and forwards too much. And then we've got just over 10 minutes for questions, so we'll have 5 minutes-ish for Adrian, and then we'll come to Vidya. So if anybody has a question, you can either just put your hand up in the air if you're in a hub, or you can raise your hand on Zoom and type the question to Alex. So we do have a question here in Wellington. So there are integrated speakers, but if you can just speak up and introduce yourself, that would be great. Thanks.
I guess one of the things that's interesting in looking at the model results versus the observational results is that nearly all of the biases in the most southern part of the the ice edge, and for much of our sector, bias is actually very small. So do you have I guess what Adrian, do you have a comment on what observations you're bringing to the table here that would particularly help us with that most southern part of potentially ice edge in Scotland and the Ross region? I'm just thinking about what Vidya showed from both GA6 through to 7.1. Much of the problem seems to be outside of our sector.
Okay, so I think the question, because it wasn't super clear, to be honest, but I'll say I think that the question was what is the Cloud and Aerosol project adding associated with the fact that the shortwave bias is maximised near the sea ice edge. I think that was the question. And so obviously the Tangaroa voyage, Tangaroa unfortunately can't go into sea ice, but we can get close to it. The Nathaniel B. Palmer voyage, the Piper's voyage, actually went into the sea ice in winter. So we actually do have measurements with weather balloons, laser ceilometer, weather radar, inside that sea ice zone as well. So we have collected data in that region. The voyage that Wolfgang Rack at University of Canterbury is involved in, that we're going to send some instruments to as well, that will also be going into the sea ice back in the summer. So we should be able to make measurements in that region as again in the coming summer. So we do have a detailed range of possibilities for making measurements. And one of the things that I would identify, if you have a friend who has a boat that I can put an instrument on, we'd really love to talk to you.
Thanks, Adrian and Michael. Do we have any other questions for Adrian? There's an eerie silence, Adrian. Must have intimidated everyone. Nope, we have a question coming through.
Can I ask another one then?
Just, yeah, after this one, is it a question? It seems to be a bit of a long paragraph. So, yes, you can ask another one with the microphone. Adrian, you're muted at the moment. Sorry.
So I can see the question from Catherine on the group chat, and it's asking, do we need geoengineering to reach the Paris targets? I'm not sure that I honestly know that answer, Catherine, to be honest. I would say that some of the climate simulations that we've run, associated with the representative concentration pathways, do require geoengineering for us to meet those targets, and those have certain temperatures associated with them. And I know that the lowest representation concentration pathways require geoengineering solutions, but I'm not sure I can say anything more than that, Catherine, because it's possibly a little bit outside my expertise. Thank you for the question there.
Yeah.
Sorry, Michael and Adrian, I guess the Vidya's hypothesis is around supercooled water in the upper atmosphere. What are the observation sets that we can apply to that problem? Seems like a hard thing to observe.
So yeah, okay, so yes, supercooled liquid is very hard to measure. So we were hoping to use the UAV to. We've got some homemade sensors that we've built up that could potentially measure supercooled liquid in situ. You can use LiDAR systems, so with polarization, you can see the difference in terms of light scattered from spherical water droplets and from complicated ice particles. So you can see supercooled liquid, and if you know the temperature, then you can tell that they're supercooled as well. So satellite observations can see them, remote sensing observations from the surface can see supercooled liquid cloud, and there are some in situ measurement capability or possibilities, but it's very difficult to do. So you've got to use UAVs or tethered balloons unless you want to lose your expensive instrument. And we tried those on the Tangaroa voyage in March, and they, as you saw from the video, they were partially successful.
And that 93% of the time was cloud cover, and most of that was below 1 kilometre by the look of it, or 1.5 kilometres. I presume the kilometre is not actually going to see that most of the time.
Sorry, I didn't hear that. You'll have to repeat that.
Sorry, you were saying that some of the ground-based instruments can see it if there's no cloud, presumably, but you have cloud for 90% or 93% of the time, and it's all low cloud. Yeah,
but the satellite-based instruments can't see the low-level cloud very often, so that's why we need observations from the surface. So the ceilometer observations that I showed in about slide 12 or 13 clearly shows that we can see the bottom portion of the cloud from the surface very well. And we've also got a micropulse LiDAR that Richard Querrell at NIWA was running that's got almost exactly coincident observations, and shows very similar results. So we're pretty confident about being able to tell the difference or being able to see low-level cloud and supercooled liquid water cloud as well. From ground-based observations, it's hard with satellite-based observations, as I identified.
Okay, thanks for that, Adrian. So we'll just, can we bring, is it a question for Vidya or a question for Adrian?
No, for Adrian.
Maybe I'll just ask first if there's any questions for Vidya, and if not, then we'll come back to you. Do we have any questions for Vidya and her part of the presentation, particularly?
Oh, there's a question, Suzanne.
So we do have a question. Do you want to come up to the microphone, Vidya?
Yeah, I'll just come.
This is a question from Suzanne Rosier. It sounds like the Southern Ocean radiation bias has been most improved by setting ice deposition completely to zero. Could a good next step be to increase this slightly and experiment with a different parameter? What would be the next best step, I suppose?
Yeah. Thank you, Sue, for the question. So we did try different realizations by using, the results that I showed you was by using 0.5 for so theoretically, turning off the deposition and changing the ice shape parameter kind of has the same effect. So it's directly, it's kind of proportional to the ice formation. So we do have a couple of realizations like changing to like 0.25, 0.75, but then to which one is the one that is to be taken as the final approach? We need probably a bit more of backing from the observational side to actually figure out, but I think a safe bet would be to start with 0.5, which is like the half point value of what is actually used in the model. That's actually the starting point. Yeah.
Thanks, Vidya. We're just going to invite Otago. We've got someone from the University of Otago that has a question.
I don't know. Okay, can you hear me?
Yes.
Oh, cool. Okay, thanks. I had, I guess it's just three things that I wondered if how they were being looked at in the atmosphere model. So firstly, there's different parameterizations used for whitecaps in the ocean, because obviously that affects the reflectivity. And I know in weather forecasting, the Southern Ocean's always been a problem with parameterization of whitecaps in the ocean. So that was one thing I wondered if how that was being done and looked at. And the other thing is precipitating snow has recently been shown over the Southern Ocean to significantly affect the reflectivity of the atmosphere. So not snow that's landed, but as it's precipitating, so when it's not a cloud anymore. And I wondered, I don't think, maybe you know better than me, but don't think that's in GA 7.1. So I wondered about if you're looking at that. And the third thing, sorry, was just that I know that there are global parameterizations of or representations of the spatial distribution of ice nuclei, both their spatial distribution and the particle size distribution of those ice nuclei, that you need to use for your a priori information for interpreting satellite observations of cloud. And I wondered if that's a good source of information because there's been a lot of validation work done there from the International Satellite Cloud Climatology and so on, if that was being looked at for climate models as well, or if we're starting from scratch there.
Okay, so I'll try to kind of recapitulate what you were saying. You'll have to guide me through. I think the first one was whether you were asking how different is it in terms of the weather prediction model and the climate model. Yeah. So I think the main difference that is lying there, or as of now, the focus that is being done is with the terms of the microphysics scheme that is being used in the model. With the current, so you need something like this, how do you call it, the double moment. So I'm not going into the details of it, but it's, so you kind of use or the focus are two entirely different kind of microphysics schemes for the global climate models and the weather prediction models. That kind of, so the same treatment, whether or not by changing this fix in this shape parameter, would it help in the weather prediction model, is something which we are trying to do by working closely with the model development team there. So hopefully we should be able to find an answer for that. And the second one, what was it? You asked precipitation of snow.
Oh yeah, precipitating snow as it's falling. I'm going to have to go though, because this room was only booked until now, so I'm going to have to go for an exam. But I might email you. It might be quite good to.
Oh, okay. Yeah.
Sorry.
Okay. Thank you. Yeah, it's just close to 1 o'clock, so I'm sorry if you didn't get to ask questions, but feel free to email them through to Vidya or Adrian or Alex. Yeah. And thank you very much again to our speakers. It was great to have a joint presentation. Thanks all for coming, and see you at the next Deep South Challenge seminar, hopefully.